Yeah. Yeah, downtown.
What's going on in downtown today?
Pretty standard. Oh. All right, let's start since it is the official start time. So welcome to CHEM 104, and we have everybody here today. And so first, so I don't really go through the roster that much, but let's just go through that. So we should have everybody, and then there is one person who is joining us either remotely or asynchronously, and I'll talk about that as well, how that works. Let's just go through the roster. And the other thing is, so I was noticing, because you need to be registered for the whole Chem 104 package, and that means that you need the lab, lecture, and recitation, and 2 people are not registered for recitation. And so that's not a big deal. You just need to add it. So let me give you the code. So the recitation code is VMQA. And again, that's only 2 of you. And I might yell out if I find it. All right, Charlene. And I know I saw some of you this morning, but just remind me if you go by something else or you have another name if I didn't see you. And then I think you went by Cammie, right? So Cammie's here. Caitlin, where are you at? Cheyenne, we were here this morning. Evelyn, she might be my remote one right now or later. And she needs to register. Okay, Andrew, but you went by Heston, so Heston's here. Anna is over there. Hannah, welcome. Isla, over there. Dagan, is that how you pronounce it?
Yes.
Okay. And Emma.
Here.
Malia, you're in lab. Taylor. Brooke. And Shelby. And Sky. And I was going to call out. So Taylor, it looks like you need to join.
Yes, I do. Is that on Blackboard?
Yeah, you have to go through back when you like register with your classes. So you can just like add it to your cart. Yeah, and just use the code. All right, and so let's go over just a few things with Blackboard. And so I sent it out as an announcement. So I sent it out right now. So this is where I live stream. Well, I've never heard that noise before. That's interesting. And so you can find past videos here. So of course we're streaming live. So there it is. You can join. So this is convenient. You know, if you're sick or whatever, you have work and you can't make it in person, you can join live, or you just want to re-watch it. It's available. So I've kind of kept doing it since people like it. And then you can, yeah, and unfortunately I don't put them all into playlists. I should if I was more organized, but there's only so many hours in the day. But you can still just go to the live and look through the past archives. And of course you could see all my other classes. What else is there in Blackboard? Oh, sorry. Let's go back. And so I try to give everything to you guys so you don't have to be in Blackboard that often. So let's just look at our syllabus first of all. And if you were in lab this morning, you got a preview as to why my syllabus, oh my gosh, what is this integration error? Are you kidding me? Okay. Maybe it's mad at me because I'm in preview mode. I just didn't want you to see all my junk. All right, now it loaded. And so blah, 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 pretty self-explanatory. So of course we have our lectures. And then if you notice, so what we'll kind of do is we lecture for 2 hours on Monday. And then Wednesday we have the recitation time. So I'll lecture for like an hour. And then we'll do the quiz. So usually recitation is just kind of meant as extra math practice time for like chemistry and physics. Usually I have it as like our quiz time happens during recitation, but then it's just kind of an hour available to ask questions or get whatever help you need, do problems in class. And then of course we have our lab Monday and Wednesday. And so there's only 16 of y'all, and they gave me 2 lab sections. So if you ever need to switch back and forth, it's not a big deal. So you don't really need to check with me on that. So that's kind of nice. Email is the best way to reach me. I'll write this on our lecture notes as well. So blah, blah, blah. So grades. So this is what your grade percentage is made out of. And so we won't have a lab practicum. So usually there is, but I'm kind of switching things up. And so if we look at the syllabus, it looks like I have no idea what's going on. But what's happening, and so like I explained to the morning class, is I have jury duty potentially on this week. So they have slotted me for like the whole week. I hope that it doesn't take the week. I don't know what's going to happen. I've never been to jury duty before, especially in Oregon. So I'm trying to just basically build up a buffer so that if we need to completely miss this whole week of lab, then we can do it. So that's why everything's kind of crammed. And if you were in my morning section, then you got a taste of that, and so many people started lab 2, so that was really good, and we'll just keep kind of working with that. So next week, we'll do labs 2 and 3, hopefully. And then I have this extra presentation, and so part of what I do, other than too many things, is I'm the Earth Club advisor, so if you want to join Earth Club, let me know. But we're doing our Earth Day celebration, so it's April 22nd, 11 a.m. to 2 p.m., which if you notice, right, that's during your class time. And so to accommodate that, I'm going to have y'all do an Earth Day project presentation, so that's going to replace your lab practicum. And so I've allowed space for that in our syllabus, so the week before, you'll do your Earth Day project prep, and we'll kind of talk about that. So kind of the idea for that is we'll have visitors on campus, so we're inviting the community to come. We'll have other outside vendors, but then I like my science classes to do kind of little hands-on demonstrations for, again, people that can come. And so the idea is like easy hands-on chemistry. So some ideas would be like red cabbage, pH, making like a slime, so that's pretty easy. So anything like that, so slime, bath bombs. You can make like silly putty or those Newtonian fluid, you know, the cornstarch stuff. And so I'm at least mentioning it to you now so you can kind of start thinking about it and what kind of, you know, little mini project you might want to do for, again, presenting to the community. Week 3, we'll have time for that in lab to kind of get everything down, and, you know, you can work with partners, so think about, right, how you might want to partner up with that, and then we'll present that on April 22nd. So that'll kind of take place of class, and so that will kind of shuffle around, again, our content because of that. And so let's just kind of look at other things, so how the class works. And so laid out for you, so I have this week's homework, so y'all can grab that when you have a second. And then I have the lab, so of course if you were in lab this morning, you probably already grabbed it, but if you have lab on Wednesday, you can pick it up then. And then I'll hand out a periodic table, so this is handy. And make sure you have your cardstock. And then if you need more, I'm happy to give out more. And so the other thing is I'm pretty generous with the notes. So I let you use open notes. So most of my tests are open. Everything I just ask that you don't Google.
I love you already.
But you still might want to write, you know, key formulas, key ideas on this kind of cheat sheet. So this is kind of your cheat sheet. And so we'll have, so this welcome assignment, we're going to do this during our recitation. So this is going to be our first quiz during our recitation period. And then what we find is that we'll have our week 1 quiz next week. So right, we'll cover week 1, and then your quiz on Wednesday will be over this week's material. And then so on and so forth. And then in general, the labs are due about a week later. And you'll find that I'm not too picky about deadlines. So, of course, right, we have to get everything in before grades are due, which is what, June 12th, 15th? I have to look at the calendar. Yeah, and otherwise, right, dates are just trying to keep us on track to, of course, finish the course, right? Because if you try to do all your assignments that last week, probably won't work out. But like I said, I am flexible to help you. And so I'd rather, you know, you you have an unfinished lab, I'd rather you just take the extra time, get extra help, and turn it in later than trying to rush and give me something that's not complete and not your best effort. And so that just kind of repeats, homework, quizzes every week following that. And of course, week 5 is the exam. Well, where I'll probably be on jury duty, but again, don't know what's going to happen, just kind of giving you a heads up. And then just continues with our labs and quizzes all the way up to the end there. So pretty straightforward. And so other tidbits. So I don't care what edition of the book that you guys have. I think I'm using like the 2nd edition. So this is the General Organic Biological Chemistry book by Janice Smith. And so what's confusing is, if you have the textbook, that's like a custom print that we have ordered. And so it's only chapters 1 through 9 of the full Janice Smith book. So that's what our library sells. I'm not supposed to tell you guys, but of course, right, you can go to Amazon and just look up Janice Smith. And then not the organic chemistry, but the GOB. Oh, that didn't. General Organic Biological. Sorry, I can't spell. And so I would just pick whatever edition of the book you can find the cheapest, right? So of course there's a new edition every year. So just whatever you can find that's
now,
cheapest.
I've been told the library will buy them from you at the end of term if you don't need them. Is that true?
I'm not sure.
I feel like I heard that from somebody and I was like, that's cool.
Yeah, because the other thing with our textbook is like there's no codes or anything, so there's no like one-time use codes. I don't like to do all that. So the other thing is, so if you don't want the official book, so I never reference the book really. We don't have problems from the book. And if you're just taking this quarter of chemistry, I might suggest looking at this OpenStax textbook. And so if you can go to chemistry, and this is also fun. So not that you guys would be interested, but this is a free OChem textbook as well online. So that's kind of new. But I recommend this Chemistry 2nd edition, Atoms First. And of course, it's not going to align perfectly, but it still has everything you need to know. So it starts off, phases, measurements, all the stuff that we're doing initially. And so that's just OpenStax chemistry. And so this would be sufficient to get you through the course. Again, all the content that you need is in there. And blah, blah, blah. So let's see. There's a few chapters in here if you're still awaiting your textbook. So chapters 1 through 4, in case you're still trying to work on that. And then under each week, I have, our lecture notes. And so if you go to the lecture notes, sorry. This is what I was looking for. So this live notebook link, so this is a live view to whatever I'm drawing up here. So that gives you your updated notes. And so that's more convenient for me. And you're not bugging me, because I used to not do it this way, and then students would be emailing me, please post the notes, but now you have them live and updated. And there might be some old, just like archive stuff hanging around. And then you should be able to find the PDF versions of the homework as well in labs, but again, you shouldn't need that. All right, I think that's it. Anything else I should cover in the beginning? Any questions of just like how this course runs or anything? Office hours, that's a good question. Generally my office hours are like after class. So I have a schedule posted, so I have to see what I put as my official office hours. So usually I just say after class. And so I also teach classes on Tuesday, Thursdays, but you could try to hunt me down like during like lab times of my other class, so that would be like in the afternoon. I have lab from 1:30 to 4:20 in the same room that we guys have it in, so 312. So you could, stalk me, hunt me down. Otherwise, just email me, and I'm more than happy to meet with you. And so that's in person, online, whatever. I'm available. But yeah, I'll try to post my schedule on Blackboard so you have that schedule. But like I said, generally after class or Friday's work.
Do you have a certain time when you check your email?
I'm a millennial, so
Okay, perfect,
yeah. All the time, unhealthily, is how often I check my email.
Feel that. Me too, bro.
Yeah, so email is the best way to reach me. Like, some people try to Zoom phone call me, and then, like, my Zoom phone doesn't work. Zoom is most unreliable, but email I will respond to. Any other questions, comments, concerns of the logistics of the class or anything? All right, so let's start diving into it. And we have, so what is chemistry? And, well, let's first kind of get a survey. So why are y'all in here? So why chemistry? What do you guys want to study?
It's one of my prerequisites for
So-
my career.
So what's your career then?
Getting into sonography, so ultrasound tech.
Oh, nice. So ultrasound, so let's put that with medicine, right? So
I'm also going into medicine,
physical therapy. And so, right, we could think about what kind of isotopes are used for imaging. And, physical therapy, you probably just want to have a general knowledge of the body and body chemistry, how things work, maybe even materials, and have some understanding. What other majors do we have?
dental hygiene.
So dental hygiene, put that under medicine. So that's also, again, really good, just thinking about what's our teeth made out of, the reactions even that happen. What else do we have? Other careers, interests. About over there.
It's for high school.
So just completing, but then what do you want to do after high school?
Business.
So business. So let's see, where's our business? So they don't have business on here, but I would put that, because we can think about, regulations. How do you run a business? How are you sustainable? Whatever you're going to produce. So that could go into a lot of different things. Sustainable, navigating regulations, all that. What other majors do we have? And then what are you going to do with it? I mean, you have everything here. So, right, depending what you want to study, like agriculture, water rights, like anything gets into chemistry. What about y'all? So X-ray as well. What about you? What? Like food science, basically, like dietitians. So that's good. So that gets into calories and nutrients, breaking down our foods to the molecular level. All right, let's hear from this side. What do we have over here?
I just plan on being a pilot, so I don't know if that would fit in anyway.
So pilot. So I like that because, right, you want to think about, again, materials. What is your plane made out of? What is it coated to prevent, erosion? So there's a lot of things. I was actually just talking to, what is it, Erickson Airline or something. And they're trying to solicit my help in, like, all their chemical baths because they have all these, like, I'll call them magic solutions, essentially, of their, like, nickel plating and cadmium plating. And so, right, they have to plate the materials for planes. So that's kind of cool. And they're trying to figure out how to maintain their baths better. What else? What other careers? Anesthesiologist, so that, I can't spell that, so put that under medicine, so again, more drugs. What else do we have? Psychology, put that under medicine. And then psychology too, you want to think about, do you want to do human trials? And that's kind of cool to get into like that part of psychology where you're getting like more deep into it with like hard science, running trials on people, studying brains. What else do we have? Any other? Art. So art would also be really important. So of course, right, all the paints are different mixtures, so they would be colloidal mixtures. And probably now working towards how to get safer pigments. You could also go into like tattoo pigments if you want to go. So that's another concern, safety concern with those pigments. Any other thoughts on chemistry? And so of course, right, I like chemistry. So I got a PhD in it, so I really like it. And again, I'm biased, but they have chemistry here as kind of a central science, and a lot of people think of it like that since, again, it's related to all these different topics. So, right, hopefully you found at least some glimpse of the connection to your future. And then, of course, related to math and physics, but this is not as cool maybe as the direct applications like you guys are proposing. And let's see, what else can we talk about science here? So geochemistry is, of course, always good from just studying, right, our history here, lots of lava tubes and volcanic activity, history. But you could also get into, of course, like oil industry. And so we have agriculture. So this is huge, of course, in chemistry. So big ag. So I put a lot of money here. So this goes into like fertilizers and pesticides. And so I have many friends in the ag industry, so big ag. And then many of you, of course, mentioned that you're related to medicine in a lot of ways, so that was cool. And of course, we don't have big pharma on here, but I should have put pharma or drug development. So that's obviously a lot of money there. A lot of organic chemistry. And of course, right, chemistry is also related to nuclear chemistry or just thinking about energy. So lots of big picture ideas. And let's see, so some people mention business and other things to think about that. Again, we all live in the Rogue Valley, so how can we keep our food and water supplies clean? How can we make that sustainable? And you can even think about going into law with that. So I'll put anywhere from patent law to environmental law, so lots of different pathways. So patent law is useful, so you just like examine patents from other people or look at litigation. And then of course environmental, that's always interesting, just figuring out regulations and how they apply, or studying case law like how they eliminated DDT. So of course chemistry, important. But what is chemistry? And so it's just defined as the study of matter, which is, of course, kind of anything. And so matter we'll define as anything that has mass and takes up space. And we'll kind of get into this. So matter can change from one form to the other. And so it can change in either a chemical reaction or they'll actually be rearranged. So we'll get into this deeper. So atoms rearrange, and so they make a new substance. And so you probably are familiar with at least some examples. So if you take propane or any sort of other combustible gas and then you burn it, so that's always converted to carbon dioxide and water. And then I'm sure you guys have seen some physical changes, and of course our classic example is ice, so I'm sure everybody has seen ice. Of course our solid water, and we can take our ice out of our freezer, let it sit there, and then it'll melt. And then we can, of course, take that and boil it on our stove. And then, oh, please interrupt me with questions and everything, especially, I always feel like the beginning part of chemistry is really difficult. And I always tell people, it's almost like you're learning a new language, right? There's all these like symbols and all these things. So ask questions, especially in the beginning, but always, but don't be shy. And so let's go over this. Again, you probably have seen this. And so we'll just be focusing on the 3 normal states of matter. So solid, liquid, gas. And so we can distinguish between these. So if we look at our solid matter, so in general, our particles are packed really tightly and fixed in place. And of course, with a solid, we want to remember, so there's still molecular motion, and again, we'll get into that. So your electrons are still circling, your atoms, they're still vibrating, but they can't actually slide past one another. And then, so if we take a look at liquid, again, at our subatomic level, so now our particles can move past one another. And so solids, usually we say that we have a fixed shape and volume. And then liquid, so liquid would still have a fixed volume, but now, right, obviously it takes a different shape. So you guys have seen that, of course, pouring water, and you of course know that, right, you can't compress it. So 10 mils is still 10 mils. But again, right, they can slide past one another, so they have some more freedom. And so now when we get to the gaseous state, so more energy has been put in, and now they're widely spaced far apart. And so usually we say gases have no fixed shape or volume. And so often we say that gases are compressible. So gases are compressible. And so that just means, right, that your gas can be condensed down. So maybe it's condensed down to a liquid. So I don't know if you guys have seen like those big liquid nitrogen tanks. So this is liquid N2, kind of confusing since it's not really a chemical abbreviation. So liquid nitrogen. So you can compress, right? So we have nitrogen in the air that we breathe. So our air is like 78% nitrogen or something like that. And then, of course, you can condense it down to a liquid. So compressibility of gases. And so this is just the words that kind of follows. So like we have just seen, right, in our solid, our atoms or molecules were tightly packed together in fixed locations. And so again, we said fixed volume, fixed shape for our solid. And it lists some examples. I'm sure you guys could go on and on. So ice, aluminum, diamond. So liquids, again, we saw that they flow and then take the shape of their container. So of course, water and alcohol, so that could be both ethanol that you consume or also, rubbing alcohol, isopropanol, or many of the alcohols are liquids. Gasoline, so that's a mixture of hydrocarbons at a certain burning point. And again, gaseous, so like we mentioned, they are compressible with our nice little graphic. So they're showing, right, solid, so we can't compress a solid or a liquid, but then that gases are. And so something else that we want to be able to do is identify matter and classify it. And so we have different ways to classify it. So element, compound, and mixtures. And so let's go through all this. So we have this flow chart. And so the first distinction is it one type of particle? And so anything over here, and it kind of makes more sense if we go down to the next sub-level. So anything that's a pure substance is either an element or a compound. And so it's kind of easier to look at, well, what's an element and what's a compound to define what a pure substance is. And so let's just start with an element. So of course, right, an element is anything on your periodic table. So that's really helpful, right? So if you're not sure, check the periodic table, right? So if it's on there, okay, it's an element. And so things that can be confusing though, and so let's write down other elements. And let's actually identify them. So I'm going to go over to my periodic table here. And so the first thing that confuses people with the elements is what we call our diatomics. And so the diatomics, all this means is that we have some gases, and in their elemental form, so like how we find them in nature, is they're bound to one another. And it's probably easier if I start on the chart. And so I'll highlight them. So I might highlight them as well or circle them. And so hydrogen is the only one that's by itself. And then the others make this little pattern. So nitrogen, oxygen, and then a lot of the halogens. So fluorine, chlorine, bromine, and iodine. And so there's 7 diatomics. So 1, 2, 3, 4, 5, 6, 7. So again, I would mark those. And so the point is they're still considered pure elements. So even though there's 2 of them, it's the same type, so it's still in its elemental form. So it's just an element that exists bound to itself in its natural state. So what we call its like elemental form. And we'll kind of get more into this, but basically what we're saying is you'll never find hydrogen like that. So that does not, at least not commonly. So does not commonly exist. So this isn't really stable, but rather hydrogen bonds to itself. And so all the diatomics do something similar. But I don't want to get too into it because we'll have to revisit this when we get into like covalent bonding and drawing Lewis dot structures. But at least for the most part. And so I'll draw another example. And so right now this might not make a lot of sense. So this is what I mean with chemistry, is right away we have all these dots and stuff. And we'll come back to what this means, so I'm not trying to jump the gun on everything. All right, so other elements that confuse people. So we also have these things called allotropes. And so allotropes are just defined as different geometrical arrangements of one type of atom. And this will make more sense when we look into some examples. And so again, allotropes, still an element, so that's kind of the key point. And let's go look at some allotropes. And so don't use Wikipedia for like current events or anything, but Wikipedia is pretty good for science. So if we look at allotropes of carbon, so carbon has the most famous allotropes. And so again, right, just different structural rearrangements. And so let's go through them. So A here is we have, again, these are all just carbon. So this is carbon in a tetrahedral arrangement, and so this is diamond, at least I believe it's diamond. So, and they're labeled down here, so this is diamond. And so then B is graphite, and so graphite is obviously what you write with the pencil. But looking at this picture kind of helps explain why that is. So the difference why diamond is so strong versus why you can write with graphite is that graphite is in these little sheets, and so it's really easy to shear off in layers, and so that's what happens is that it's really weak, and then that allows us to write by shearing off our little graphite. And so then this one is Lonsdaleite, but I'm not too familiar with that one. D is interesting, so this is buckyballs or C60. And so this led to the development of nanotubes. So they started making different material with this nanotube. So they won a Nobel Prize for the discovery of the buckyball. And then so the buckyball led to H. So H here is our carbon nanotube. So now this is a new material that they're making lightweight material out of, since it's hollow and has strength, and other research areas with these nanotubes. And so that's carbon. And so I would probably write that down as some examples. So we have carbon is an allotrope. And again, I would write diamond and graphite. So those are different forms. And I'll put C60, again, not inclusive, but it's still an element. So that's the key point. So if you ever see C60 on the exam, still an element, still one type of atom. And so let's look at other allotropes just for fun. So these are the more common ones. And so phosphorus has some allotropes that, of course, people are familiar with. And so, of course, white phosphorus is, that's the one that's used in war. So this is the structure of white phosphorus. So that is highly flammable and pyrophoric. So it ignites with contact with air. Again, hence why it was used in war. And so then other types of phosphorus. So red phosphorus is formed from white phosphorus. So again, just different structural arrangement. And then there's also violet phosphorus. So just, again, different structures. And black phosphorus is the most thermodynamically favorable form. So that's interesting. And sometimes you might see P4 written out to show that it's an allotrope. So you might see P4. So again, this is just allotrope. Phosphorus, so still an element though. So still just emphasizing, right, these are just elements.
And you said the diatomics were still elements as well?
Yeah, exactly. Yeah, so good to understand it. And then the other one that comes up a lot is sulfur. And so sometimes you see people write the formula for sulfur as S8. And so why they do that is because sulfur is actually found in this ring form. And so, again, that's why they call it S8. And so that's what it looks like. And so I'll write that as well. So S8. So again, just an allotrope of sulfur, but still elemental sulfur. And so there are more allotropes, but those are just kind of the main ones that you'll see. And of course, your diatomics. All right, so now that we established what an element is, so does anybody have a guess what a compound is? Yeah.
Kind of like water, H2O, so two together.
So 2 or more atoms. And then you mentioned H2O, but what's kind of the key form of that? You have H2O. Because there's a second part to this definition of what a compound is. And you have the right idea.
Is it the type of bonds they
No, but I'll just give it to you. So defined ratio, or defined chemical formula. And so that would be, H2O, and so now we always get into drug chemistry. And I don't know why I always think of this first, but so you know how you guys are young, but so are you guys familiar with like dabs, like the weed stuff that they make into this gooey thingy? And so why I like to bring that up is, so right, a dab would be our mixture, right? But then it's important to define, so everything that's in that dab, so that could be, right, THC. So, right, that would be a defined chemical formula, THC. And we know it's defined, so I'm showing the structure. And, right, it has our formula, so this is defined. And then all those other compounds, so limonene, if I could spell limonene. So limonene is a common terpenoid found in like those dabs. And so again, right, that's your defined chemical formula of limonene. And so there's, of course, other aliphatics, so all these terpenes give you kind of the flavor. So all these are specific chemicals. And so we could go on, so I don't know all my drugs that well. But like, so cocaine, right, that's a pure drug. And then, so what's the one where like it's cocaine cut with something? Yeah, crack. So then crack would be a mixture, right? I know. And so welcome to chemistry, drug the class. Yeah. So now you can go home and tell your parents all you learned about chemistry now. But it's important to make that distinction. So like the other, let's think of more Alka-Seltzer. So this is another mixture. So Alka-Seltzer itself, let's see if I can find one with the ingredients. Ingredients. Yeah, so this is the one I was thinking of because it has acetaminophen in there in your Alka-Seltzer. So the Alka-Seltzer is a mixture, right? And then it also, they're not showing what else is in there because there's like baking soda and citric acid to make it fizz. And so, right, these are all the chemicals. So acetaminophen is a chemical, right? Chlorophenephrine is another chemical. So, right, all these are chemicals versus Alka-Seltzer being the mixture. All right. So now let me write that. So again, anything with a defined chemical formula. So THC, aspirin. So aspirin has a defined chemical formula. Acetaminophen. So all those are defined chemical formulas. And so then we get into our mixtures. So then our mixtures, all we have to determine is it heterogeneous or homogeneous? And the way to kind of think about it is the first bite the same as the last? And so if that's true, right, it's homogeneous. And so now I'll put in there, so dab mixture. So, right, that should be homogeneous, although now we're really going to get into it. So, I don't know, now I'm just talking too much about dabs. But you know how dabs, how sometimes they like crystallize out? And so, right, if they crystallize out, so now it depends like how your mixture works. And I only bring it up because I assume it's so common now. And so, right, so now you can have a heterogeneous mixture. So if you have little crystals crystallizing out, depending how pure your mixture is, and then if it's still sitting in some goop, right, I would consider that heterogeneous. Whereas if it's just all the same throughout, that's homogeneous. So other good examples, so let's talk about ice cream. That's a little friendlier. So like cookie dough ice cream, so that would be heterogeneous. So you can have one bite that's full of cookie dough, and maybe the next is not. So cookie dough ice cream. Usually people think of like salad dressings too as good heterogeneous mixtures where they got chunks in it, and usually there's some oil water mixture anyways that's not very miscible. And then so anything homogeneous I would also put under there, so they did tea, but any sort of drinks like Coca-Cola, the drink, Coca-Cola drink, so not cocaine. Important distinction in this class. Yeah, so rum, right, any of those homogeneous mixtures, Gatorade. Right. Any other thoughts or examples of mixtures or compounds or questions?
Yeah, on the T one, so like if the T bag were like break and then there were little things that would be the hetero?
Yeah,
Okay.
yeah, exactly. And so if you're on an exam and you're not sure, like just, write out your thinking to the side. Because, yeah, you bring up a good point. Because, like, are there particles in the tea? So that's always a question. Cheese is another good example. And so that depends. So if it's just like cheddar cheese, right, that's probably homogeneous. But then heterogeneous could be Swiss cheese with the holes, or like a jalapeno cheese, or a blue cheese, right? Anything where it's kind of different uniformity. Other thoughts, ideas, examples? All right, so let's keep going on. And so again, this is now just the text that goes with it. And so we, again, kind of saw that. So again, heterogeneous, just different composition in different regions. And so usually think of like a sand-salt mixture where you get it from the ocean and the sand kind of settles, or anything else that's, again, not uniform. And homogeneous, I think y'all were getting that down. So again, mixed uniformly. And so the other kind of part in chemistry and what we're kind of thinking about with all these ideas and what's what is, so chemistry is how do we kind of separate stuff as well. So how do we recover our pure substance? And so that's a lot of chemistry, is distilling and pumping off and filtering. And so here's just shown a simple distillation. And of course, my first criticism is that this diagram has an open flame, so that is a hazard. So normally you don't want to distill with an open flame. So once we do, actually I don't remember, I don't think your class does distillations. But if we were to do a distillation, so now we have heating mantles, which are a lot safer. And so they just have a thermocouple. Let's look at a heating mantle. And so they just look like that. There's some sort of thermocouple in there. So I think we have this model actually for some of our labs. And a lot safer than using the open flame. So the open flame, these joints can sometimes leak, and then you'd have a hazard. And so that's how many fires have started in life. And so if we look at what is going on, so we can take a mixture, and let's just think about this. Let's just do salt water in our minds. So you can separate other liquids that have a large enough difference in boiling points, but salt water would be again, a more practical distillation. And so then you have your heat source. Again, don't want an open flame heat source. But then you heat it up, and then it goes up here. And then this is a condenser. And so this condenser has an inner part that's connected, and then it's surrounded by a water jacket. So then the vapors come up, they get cooled down, and then we have our pure liquid here. So this would hopefully be some pure water from our distillation. So it would help you if you're trapped on a desert island or something. But yeah, so distillation, really important, so it helps us separate out mixtures. And so now let's talk about units. So of course, that's an important part of chemistry. And so we have our scenario here. And so this was back in 1998. Boeing Delta II was going off to Mars. And so we'll look at what happened, and then we'll go through with why that happened. And so this little unmanned craft was sent to Mars, but unfortunately, it entered the atmosphere kind of too close, and then it blew up into a million pieces. And so that was a really expensive mistake. And so let's see what happened. And so they found that the problem was in the orbiter's thrusters and the program used to calculate that. And so the software was expecting it in pounds of force, but then the next piece of code assumed that it was in newtons per square meter. And so this was just due to a difference in teams. So yeah, it's scary. And so Lockheed Martin, they were in pounds, and so apparently they were supposed to convert it to metric units, but they didn't, and NASA assumed that it was already made, and so yeah, whoops. And so that's why units matter.
Oh man, imagine getting fired over that.
I know, I would
You
not.
know somebody got fired.
Well, you never know. Like, people get away with stuff, but yeah, it's yeah. But all that to say is that's why, right, units matter when we're doing it in lab. So no matter what you're measuring, meters, centimeters, just write it down so that we all know. And so the other thing is, well, science deals with a wide range of things. And oops, so just for fun, can anyone guess what the size of a human hair is?
0.01 or 0.02 millimeters.
I think that's pretty close. 0.02 millimeters. That's a good guess. So hair is on the micrometer scale. So 1 times 10 to the negative 6 is micro. So that's pretty close to what your guess was. And then what about the size of an atom? Any guesses?
Way smaller than the particle of human hair.
So way smaller than the hair. Any thoughts?
Fold a piece of paper in half, like 30-something times.
And then what unit would that be on? Any guesses? So it is actually on the nanometer scale, roughly. Yeah, so it's either roughly on the nanometer scale. So nanometer is 1 times 10 to the negative 9th. But actually, so sometimes you'll see this other unit. So they also use what's called the angstrom. And so that's 1 times 10 to the negative 10 meters. And so this is just a chemistry unit, the angstrom, but otherwise nanometers is about the scale it's on. And then what about an elephant, or like how many tons it weighs, or pounds? 10 tons, I feel like that's a little big.
I was gonna say like 6 or 7.
I thought it was like 3 tons.
Yeah, I think it's,
Oh, what kind of elephant are we talking about?
any elephant.
So just,
So let's see.
2.
So about 2-ton scale, probably. So tons, I don't know how high they get, probably 6 tons or so. And so what is that in kilograms, maybe? So anywhere, right, 2,000 to 6,000 kilograms or more. So pretty large scale. And then what about distance to the nearest star?
Is it time 1,000 kilograms?
Are we counting?
A ton is 2,000.
Oh,
So yeah, I don't quite have it. I just kind of put some rough estimates on there. So what's the distance to the nearest star?
93 million miles or so-ish.
Nice.
90 some odd million miles. If you're counting the sun. If we're counting another star, it's a lot farther than that.
Yeah, so where's the next nearest star? So several light years. So I think it's 4.35 light years. So light years, which I have is roughly 2 point, oh no, I wanted this in kilometers. So, so 4.115 times 10 to the 13 kilometers roughly. So pretty large.
What's the equation below the nanometers represent?
Oh, this little A here?
Yeah.
So this is an A with a 0 on top, and that's angstrom, and that's 1 times 10 to the negative 10. So we won't talk about it too much in this class, but it may come up, like if you look at chemistry stuff, they like to use this unit for chemistry specifically. And so now let's get into the metric unit. So this just kind of gives us a taste, right? So now we can see, well, scientists can work from anything that's really small to really large. And so, of course, we have our metric system to help us deal with that. And so we have all our base units. And so these are our base units. So length is in meters, mass grams, volumes liters. And then, so they have temperature as Celsius, but I'm going to put in parentheses Kelvin. But again, we'll revisit this as we continue. And then time, your base unit is seconds. And then information is bytes, but again, we won't deal with too much of that. And then we also have our moles, which is our special chemistry unit, which we'll come back to. So this is chemistry unit. And so multiples of 10 are created then by adding a prefix to each base unit. And so let's look at this. And so I have 2 different charts, or not different, but they say the same thing, but in different ways. And so let's look at this one. And so if we look at the top here, so this is tera, and then it's telling us quantity in 1 base unit. And so this is kind of confusing to me because this is saying, right, how many teras are in our base unit. And for some reason that feels less intuitive to me. So I like this chart, and I actually might go run and print some right now for you because I forgot to do that. And so this is the multiplier by the base. And I think this is easier to read. So, right, this means we have 1 times 10 to the 12 base units. And so sometimes I like to put, meters or whatever. And so what we want to practice is writing our conversion factor. And so let's slow down a little bit. And what does that mean? And so it's kind of easier to maybe think about conversion factors that we know. And so all this means is, so let's say, right, we have 12 inches in 1 foot. So this is a conversion factor, so we can write it like this. But we also want to just practice writing it in this kind of fraction form, or where we can have 12 inches in 1 foot, or 1 foot, right, is equal to 12 inches. So it all says the same thing, but as we get into our math and dimensional analysis, you'll see why it's convenient to have it in all these different forms. And so then what we want to do is, again, just write our relationships. So now this is looking at our millimeters. And so let me flip to this page. And so this is the one they did. So again, this is by the base unit. And this could be somewhat confusing, right? Because it says by the base unit. So that means we have 1 times 10 to the negative third meters, right, in 1 millimeter. Or, so they made it in all positive exponents. And so you can do that mathematically, so I'll write it over here. So 1 times 10 to the negative third meters is equal to 1 millimeter. But then if you want to make it positive, so you can multiply it times 1 times 10 to the third. So you're just multiplying it by 1 effectively, right? So 1 times 10 to the third over 1 times 10 to the third is 1. And then that gets rid of this factor here. So that gives you 1 meter is equal to 1,000 millimeters, which is what they wrote here. Makes sense so far? So let me go run and print you this really quick. Otherwise, you can start looking at it and kind of figuring it out on your own. But let's do that. So let me just run to my office and print this out so you can write this down, because this will be a good cheat sheet. out your conversion factors, and then we'll go over them.
Or do you want to start like that?
You know, like later next time.
Yeah.
I think it's up to you. Personally, I like to use all positive exponents, but they're not like wrong.
If you did want to do them with the negative exponents, how would you?
So then you have to multiply it by like 10. Yeah, so like if I did it 10 over.
So then I do one x, multiply that by one x, and then to the positive one.
Yeah, so
cancel
like
that
10 over
out.
10, yeah.
Basically.
I'll try to write them. We're trying to write our conversion factors. So we could start with this one. So tera, so this is times the base unit. So means 1 times 10 to the 12, let's just say meters, right? Would be in 1 terameter. And same thing with this one. 1 times 10 to the 9 meters is equal to 1 gigameter. So you could write that. It's kind of like
That's what I don't know how to get
Yeah, or you'll have like a negative, well, this is by the base unit. So you have 1 times 10 to the negative 12, let's just say meters is equal to 1 picometer. But then if you multiply it by 1 times 10 to the 12 over 1 times 10 to the 12, then that gives you a positive conversion. Maybe try it for like either one, like the total. We'll go over to so let's do a few together, because we kind of have a mix of some people getting it, some people not. And that's fine, right? Because we're all on different pages mathematically, so it's good to go slow. And so I'm just going to start from the top here and go over a few. So this is, again, by the base. And so we're saying 1 times 10 to the 12. And I just like to work in meters just to help us. So 1 times 10 to the 12 meters is equal to 1 terameter, or any other substance. And then we could say, right, let's just put teragram so we can see other relationships. So 1 teragram is then 1 times 10 to the 12 grams. And so let's try this for a tiny unit. And so let's skip down to pico. So now pico is 1 times 10 to the negative 12, again, by our base unit. So we're saying 1 times 10 to the negative 12 meters is in 1 picometer. And so me personally, I don't like using negative exponents. There's nothing wrong with it. You can totally do it, but when we're doing mental math, sometimes it confuses me. And so what I was saying is if we want to get rid of this, then we can multiply it by 1 times 10 to the 12 over 1 times 10 to the 12, right? So we can have, basically you can have 4 different conversion factors max. So I'll just write it out. So right, we can do it in negative exponents. So this is the same thing. Or if we like positive exponents, we can say, so 1 meter then is 1 times 10 to the 12 picometers. So does that make sense how you can take the negative exponent and then make it positive? And then of course we can rewrite this as 1 times 10 to the 12 picometers, is equal to 1 meter, or whatever, right, picoliters, picograms. And so I'll do that again with femto. So we have 1 times 10 to the negative 15 meters is 1 femtometer. We can write that relationship flipped. Or we can write it in positive exponents. And so these little units, right, we need to have basically a lot of little units in the big unit. So that kind of helps with your thinking too. So then femtometers, well, if I have 1 meter, then I need a lot of femtometers, right, a bunch of tiny meters. So 1 times 10 to the 15 femtometers is equal to 1 meter. So maybe take another 2-3 minutes to try to fill this out on your own, and then we'll just go through from the top down to fill this together.
I think I'm just a little lost on where the whole number comes into with the millimeters. Do you want us to solve it like a whole number, the 1 times 10 to the 12? Because I know that can be a lot of zeros, so do you want us to just leave it?
In scientific notation, you mean?
Yeah.
Or? Yeah, I would leave it in scientific notation. Because, yeah, you don't want to write out.
Yeah.
I was confused when you multiply to, make the exponent positive, and you multiply the top of the fraction and the bottom of the fraction by 1 times 10 to the positive 12. Wouldn't that change, like, why would the bottom still be 1 if you're multiplying?
So then this changes, the top goes to 1.
The top goes to 1.
Yeah. So 1 times 10 to the negative 12 times 1 times 10 to the 12, that goes to 1.
Okay.
And then the 1 picometer goes 1 times 10 to the 12. So that's how you get the 1 meter is 1 times 10 to the 12 picometers.
And then you just converted that one to the negative.
Yeah, so this one, if you just multiply it by 1 times 10 to the negative 12 on top and bottom, that probably is the easiest way to see that mathematically. Or I'm just thinking of like, how many, like how would you have to break up your terameters, right, to get view 1 meter, since now you need,
So you're like reversing it so you can go back and figure it out.
yeah.
Okay.
And I don't know if this is helpful to people or like more confusing putting the negative with the larger ones. But I thought it might help since this page shows it in the negative, which is kind of confusing, right? Because remember, this was saying how much is in one base unit. So that's why they have the negatives there.
So in like a lot of the examples, like you were providing a base unit with meter.
Yeah, so I just have it as meters there. But and so let's kind of fill in the rest. And so these are easier to see in probably the positive ones. So 1 times 10, so again, by the base to the 9th meters, or grams, is equal to 1, right, gigameter. Or, again, 1 giga, I'll put gigagram now, is 1 times 10 to the 9th grams. Do the negative exponents just confuse you here or help you? I don't know, do you want me to write just like one example? So 1 gram would then be 1 times 10 to the negative 9 gigagrams. Does that kind of make sense?
Yeah.
So then just,
So
well,
do you want us to do it in the meters or the grams?
it doesn't matter, just as long as you realize, right, it could be grams, could be
Yeah.
liters, could be moles, yeah. Whatever makes sense for your sanity. And then so 1 times 10 to the 6th, I'll put megagrams just for fun. And so mega, notice, right, this is a big M. And so the M's are kind of confusing because you have big M for mega, and then you have little m for milli. And then you have the weird mu, so it looks like a U with a tail on it for micro. So that's 1 times 10 to the negative 6. And so I'll go back to the top, so, oops, sorry, I wrote this out wrong. 1 times 10 to the 6 grams, sorry, is equal to 1 megameter, or megagram. Or 1 megagram is 1 times 10 to the 6 grams. Or we could say 1 gram is 1 times 10 to the negative 6 megagrams. So hopefully it's slowly making more sense. And so now kilo, so 1,000 meters is in 1 kilometer. 1 kilometer is 1,000 meters. Or we could say, right, 1 meter is 1 times 10 to the negative 3rd kilometer. You want to think about it, the negative. So deci, I usually like to just think of, right, there's 10 decimeters in 1 meter. Or like they have there, so 1 meter is 1 times 10 to the negative 1 decimeters. Oh, no, that's not right. It's equal to 10. Sorry. I'm screwing this up here. There we go. And then centis, so centis easier to think about. So 100 centimeters in 1 meter. Or again, this is times the base unit. So 1 times 10 to the negative 2 meters is equal to 1 centimeter. Then we had our millis, so again, put it in positive units or by the base of our negative 1. So 1 times 10 to the negative 3rd meters is 1 millimeter, or 1,000 millimeters in 1 meter. So micro, so I'll put it over here. So 1 times 10 to the negative 6 meters then is 1 micrometer, or 1 times 10 to the 6 micrometers is equal to 1 meter. Of course, we can flip that. And then our last one to write out, so 1 times 10 to the 9th nanometers is equal to 1 meter. Or negative, right, 1 times 10 to the negative 9 meters is 1 nanometer. All right, any questions about the conversion factors here? So ask questions. And so now the question is, well, what do we do with these conversion factors? And so now we're going to use them to convert. And so let's do a warm-up with kind of what we know. And so let's just take our conversion factor that we're used to seeing, right? So 12 inches is equal to 1 foot. And so let's say we want to convert 20.34 inches to feet. And so the whole point of this and why we spent time writing all our conversion factors is for this dimensional analysis. And so dimensional analysis is just where you kind of set up your units and then you kind of use your units to help you figure out how to get to your next unit. And so you always start with what you know. And so you can start off laying out your problem. So this is what we know, right? So we want to take 20.34 inches and go to feet. So I just put it over 1. So we're just That's our starting point. And then this middle part, that's where we put our conversion factor. And then we're trying to get to feet. So we're trying to pick our conversion factor that's going to put inches on the bottom, feet on top, right? Because again, that's what we want. And so we need inches to cancel. And so we have this relationship, which is really our conversion factor, because we could write it either way, right? So that's what we spent time doing. And so now we can pick the appropriate conversion factor. And so again, we're going from inches to feet. And so that means, right, I want inches on bottom, feet on top. So now I know to pick this relationship. So now I can put that in there, my conversion factor. So 1 foot is equal to 12 inches. And now we can double check our dimensional analysis. So inches cancels out. Yes, I get feet. And so now we can pull out our calculator and do the math. And now we have, so multiply across, so 20.34 divided by 12. And so that gives us, 1.695 for our feet. And then, so we haven't quite gotten there, but so now let's talk about sig figs at least somewhat briefly. And so we started off, so we have 4 sig figs in our problem. And again, we'll answer what are sig figs as we continue. But basically, we have 4 numbers here that we can report. And then your conversion factor doesn't count as sig figs, so this is just a relationship, so it has infinite number of sig figs. So we want to report to 4 sig figs since we're doing multiplication division, so we keep our total sig figs. Significant figures, but we're like about to get there in lecture, so I know it's kind of confusing. That's kind of the problem, is we're all over the place. And so we will report it to 4 sig figs, so keeping all these 4 digits, so 1.695 feet. And yes, we'll come back to sig figs if you're totally lost about what I'm saying. So let's try these first 3. So see if you can convert meters to kilometers, grams to milligrams, and meters to centimeters. So does someone want to put the first one on the board first, 5 meters to kilometers? Yeah, and you can do the far board over there. I think there's a blue marker. So that looks good. So I'm just going to rewrite what she wrote up there. And so starting with our 5 meters, and then write our conversion factor. So that just came from our sheet. So 1 kilometer is 1,000 meters. And so again, wrote it in this way. So meters cancels, leaving us with kilometers. And that looks good. So 0.005 kilometers. Questions about this one? Does someone want to put the next one on the board? So 3 grams to milligrams. Go for it. And you can do it either underneath or on the other board. So that looks excellent. So write what we started with, and then again picking the appropriate conversion factor. So 1,000 milligrams and 1 gram. And so again, your grams canceled. So I like that, 3,000 milligrams. Yeah.
So, let's say, for purposes of converting something with a higher exponent, so instead of to the 3, it was like to the 6 or 7 or something. When you write out, like, once everything cancels out, how do you write your final answer? It's like a lot of zeros.
Then you could write it in scientific notation. So I could have written,
Would it be 3 grams over 1 times 10 to the 3rd milligrams?
yeah, so it'd be 3 times 10 to the 3rd milligrams for this number. Yeah, so we still write whatever this number is and then to whatever power. So I think we'll go over this a little later in case people are fuzzy, but of course write positive zeros, or excuse me, positive exponents, you add zeros. So write 10 to the 3rd means you add 3, so 1, 2, 3. And so right, this one we could have written, so 1, 2, 3, so 5 times 10 to the negative 3rd kilometers. So yeah, either way, and so your calculator might also, help you, because your calculator should also do it in scientific notation. So like the first one, well, actually it doesn't, because sometimes, no, I was trying to do it in scientific notation. Now I forgot. play around with it. But yeah, usually your calculator will put it into exponents once it gets like really large or small. And so let's try, so I said do the last one. So do 7 meters to centimeters. Does someone want to put that on the board for us? You, anybody from this side?
I know the answer, but I don't fully understand the first equation and then adding the second equation.
What do you mean?
Like, I understand how to do it, but I don't understand the purpose of adding the second, not the second equation, but the second thing in parentheses.
The conversion factor?
Yes.
Yeah, I mean, the conversion factor is how we get there, though.
I think it's just like when it gets too complicated, that like you have to use it, because
Okay.
a lot of people know there's 1,000 milligrams in a gram.
Yeah.
So,
Okay.
Did you want to put the 7 meters to centimeters on the board, or are you going to do it?
yeah.
Okay, sweet. Got a lot of volunteers. I like your answer, but your conversion factor is flipped.
Oh, I see. Sorry.
In here? Yeah, so the 100 needs to go on top, and then the 1 goes on bottom so that it cancels, because you want the meters to cancel. And then it should just be 7 meters over 1, not over 1 centimeter. And then that'll make more sense. So yeah, just over 1, and then 100 centimeters is in 1 meter. And that looks good.
So does it matter if it stays like both of the ones are on the bottom when you're like converting?
Well, you're trying to multiply across so such that, right, your meters are eliminated. So in this case, right, you're dividing so that meters cancels to give you your unit
Okay.
of 100 centimeters. So I'll just write that. So right, we started with 7, and then conversion factor, so we want centimeters, so there's 100 centimeters in 1 meter. So again, conversion factor, giving us 700. All right, so take a look at this one, and then we'll go over it together. And so this one is a little tricky. And so see if you can figure out how you might do this one. So it's going from milligrams to kilograms. So what are just some thoughts? What are we thinking of how we might do this? Yeah?
You could convert it from milligrams to grams, and then you can convert grams to kilograms.
Excellent. So that is probably the best way to do that, given what we know. And so I call this a two-step conversion. And so just like he said, right, let's take it, so we have our conversion factor from milligrams to grams, so we can figure that out. And then we can go from our base unit to kilograms then. And so we can set this one up together. So 60 milligrams. And then I'm going to have my first conversion factor, right, milligrams to grams. And then, so there's 1,000 milligrams in 1 gram. And so notice, right, milligrams cancels. Oops. So that looks good so far. And so now we're at grams. And this is where the dimensional analysis part starts to kick in with this multi-step process. And so now we can continue. So now I want to go from grams to kilograms. So now I need my next conversion factor. And so now 1,000 grams is equal to 1 kilogram. And so now we can just multiply across. And so this is where you can practice your mental math. So for those of you, right, trying to think about how to write this in scientific notation. So you essentially have, right, 60 over 1 times 10 to the 6 on bottom, right? So you can add your exponents, so 1 times 10 to the third plus 1 times 10 to the third, so exponents add to give you 10 to the 6. So this should give you 6 times 10 to the negative 5th kilograms. Again, just mental math, zeros cancel. But feel free to use a calculator. You know, it's good to use mental math, but I'm also not trying to scare people away. So that also works, and then notice the calculator does spit it out in scientific notation. So 6 times 10 to the 5th, yeah.
Do you care what way we write it? Like the scientific notation or the?
No, so you could write, you know, a bunch of zeros in front, and I would count them. And so before you dash off, so we still have 3 minutes. And so I did want to bring up, so some people may want to do what I call a one-step conversion. And I at least want to talk about it, but if you don't see it, you know, don't worry about it. And so the other thing to think about is what is your relationship between milligrams and kilograms? And so milligrams is 10 to the negative third. Kilograms is 10 to the third. So you can divide them, right? There's 10 to the 6th difference between them. So you could try to make a new conversion factor and just think, right, you need more of the tiny units in the big one. So then that comes up to 1 times 10 to the 6 milligrams is equal to 1 kilogram. So, right, this is essentially your new conversion factor, which then, of course, you could use to convert. So this works as well, but like I said, if you don't see this, you know, don't stress out. It's a good trick, but stick to the 2-step conversion, right? This is what we really need to do. If you can do that, you're in good shape. If you see this, you know, more power to you. Yeah.
With that one, the second one is the 6 because you reverse the negative into a positive like we did before and then add them together to get the 6.
Yeah, essentially. Plus, I was also just trying to figure out the difference between them. So if you take, right, 10 to the third divided by 10 to the negative third, I'm hoping this works. Then, yeah, that's how I got my 10 to the 6 factors, so then I could see that. And so I'll just write that out. So 1 kilogram is 1 times 10 to the 6 milligrams, which gives us our same answer. All right, so on Wednesday, we'll continue kind of practicing these conversion factors. We'll pick up here and continue, and then talk a little bit about sig figs and temperature conversion, so that's still coming on the docket. All right, and then if you have questions, I am available for office hours today after class. Otherwise, we can chat in lab.
Thank you.
So have a good one. And then I will go ahead and stop the stream.